to our podcast where we simplify complex concepts and deep dive into topics that matter. Hello, I am Radha.
And I'm Yash. We are a third year chemical engineering student. And this is our TP mini project. And we got the topic transport analogies and engineering correlations.
So, today we are tackling an important yet often tricky subject analogies and transfer coefficients, which is a subtopic of our subject transport phenomena. Transport phenomena is very important and crucial subject for learning the chemical engineering. This topic plays a crucial role in transport phenomena, engineering calculations, and real world applications.
That's right. Whether you're a student, an aspiring engineer, or just curious about the physical interpretation of heat, mass, and momentum transfer, this episode is for you.
We will break it down step by step. First, we will explore the physical meaning of analogies, discussing how different transport mechanisms are interconnected. Then, we will dive into transfer coefficients, explaining how they help quantify these processes. So, basically, firstly, we will discuss how analogies, what is the physical meaning of analogies, and what are the restrictions, confinedness, boundness of applying the analogies in any of the situations, conditions.
That's correct. Our main topic focuses on transport analogy, which includes two majorly, that is Reynolds analogy and Chilton-Coleman analogy. We're gonna look into Chilton and Reynolds analogy in details, seeing which condition it applies and what are the major conditions, that is it applied in the gases or liquid, etc.
And make it even more engaging, we will connect these theories to real world examples. Everything from industrial heat exchangers to pollution control systems, etc. Oh, and a special treat, we have incorporated insights from a reference podcast that discuss transport analogies and transfer coefficient correlations. So, expect an exciting blend of textbook knowledge and practical insights.
So grab your notes, sit back, and let's decode the world of analogies and coefficient with us. So before starting the video, we would like to give a small briefing on how this video is going to be. We are majorly going to focus on transport analogies and two of its major components, that is Reynolds analogy and Chilton-Coleman analogy.
So the major question is from where we get these relations of transport analogies. So what do we exactly need to understand the transport analogies? So the topics which we needed to learn before learning the transport analogies is must know the dimensionless numbers and also the physical interpretations of some of the coefficients like mass transfer coefficient, heat transfer coefficients, and friction factor. You must have the good idea on these topics, then you will get a nice brief knowledge about analogies. And if you don't have much idea about it, so don't worry, we will gonna cover these topics in short in our video before explaining the analogies.
And in the end, we are going to also explore the engineering correlation, and we are going to cover few of the engineering correlation like flow over flat plate, sphere, or a cylinder.
So majorly at the end of this, you will get the engineering correlations which we use for the sphere and for the cylinder also.
Before we get into analogies and how heat, mass, and momentum transfer are surprisingly similar, let's take a step back and brush up something fundamental but super important dimensionless numbers.
Absolutely. Because if we are talking about transport phenomena, whether it's fluid flowing, heat spreading, or chemical diffusing, we're going to run into these magical terms, or you can say dimensionless number. They carry no unit at all, but carry a lot of physical meaning.
Think of them like the universal language of engineers. Dimensionless numbers, they help us compare different systems, simplify complex equations, and even predict how things will behave without doing mountains of math every time.
Exactly. So before we jump into our main topic, that is transport analogy, we would like to give a small gist about dimensionless number. We have created a 7-page PPT starting from dimensionless number of Reynolds number to many more. But the main arises is what exactly are dimensionless numbers?
Right. The name sounds fancy, but the idea is super simple. A dimensionless number is basically a number that doesn't carry any physical units, no meter, no seconds or kilograms. It's just a pure ratio of two things with the same units, so the units get cancelled out.
Exactly. And the best part, these numbers aren't just math tricks. They are powerful tools. They tell us how one affect each other in some way or another in transport processes. Like, is the fluid's inertial stronger than the viscosity? That's what Reynolds number tells about.
Or is heat moving through a material faster than momentum? That's where the Prandtl number comes in.
So why do we need these numbers? Imagine you're designing a heat exchanger or a chemical reactor. You can't test every possible scenario in real life. It's expensive and time consuming. But with dimensionless number, we can predict system behavior by scaling things down to a lab and then apply it to a real world setup.
Yep. These numbers let us compare different systems that are technically very different but behave similarly when the dimensionless numbers match.
Exactly. And they make the equation of fluid mechanics, heat transfer, and mass transfer look almost identical when we non-idealize them.
So, now that you know what dimensionless numbers are and why they matter, let's break them down one by one.
We will walk you through big names like Reynolds, Prandtl, Nusselt, Schmidt, Sherwood, and many more. Don't worry, we will explain them, what they mean, where they come from, and how exactly they use in the problems. So first, we are going to cover Reynolds number. The Reynolds number is a dimensionless number used to predict flow patterns in different fluid flow. It gives the ratio of inertial forces to viscous forces and helps determine whether the flow is laminar or turbulent. So Reynolds number is actually rho Vd by mu, where rho stands for density of fluid. V or U as in stands for characteristic velocity of the fluid, which is in meter per second. The D, or you can say L, is the characteristic length. The characteristic length may vary from a system of uh, shapes to shape. For example, in a pipe, the characteristic length is the diameter of the pipe. Then we have mu, that is dynamic viscosity. We also define mu, which is mu upon rho, that is kinematic viscosity. In future, looking at the forward of the PPT, you're gonna tackle this mu, that is mu upon rho, or you can say kinematic viscosity. We define Reynolds number into three parts. The first one is when Reynolds number value is less than 2000. We define it as a laminar flow, which is smooth or in the same pattern. The middle one, which is the transitional flow, which carries in which the Reynolds number is between 2000 and 4000. The last, where the Reynolds number is very high, creating a chaotic or eddy stream, in which the Reynolds number is greater than 4000. We call this region as the turbulent flow. In the forward PPT, you're going to tackle the Reynolds number.
So, now we are going through Prandtl number. So, Prandtl number is a dimensionless number that relates the momentum diffusivity, which is also viscous diffusion, to thermal diffusivity. It determines the relative thickness of the velocity boundary layer and the thermal boundary layer in a flowing fluid. Simply, we can summarize it as Prandtl number is just a ratio of momentum diffusivity to thermal diffusivity, which we can write it as mu Cp by K. And as we have learned in earlier slides that mu by rho is your kinematic viscosity. So we can also write Prandtl number is equals to kinematic viscosity by alpha. We can denote alpha is equals to K by rho Cp, which is a thermal diffusivity. Okay, so Prandtl number is a kinematic viscosity by thermal viscosity, thermal diffusivity. Prandtl number, if less than 1, then heat diffuses faster than momentum. If, if Prandtl number equals to 1, then heat and momentum diffuses at similar rates. So Prandtl number equals to 1, it is valid for gases and liquids also. And if Prandtl number is greater than 1, it defines that momentum diffuses faster than the heat, such as oils.
Now, moving on, we're going to explain schemate number or schemate number. The schemate number is a dimensionless number that compares momentum diffusivity or kinematic viscosity to mass diffusivity. It shows how quickly momentum is transferred relative to a mass in a fluid. We have a relation of schemate number as schemate number is equal to nu upon dAB. Or from the previous slide, we have learned that nu is equal to mu by rho. So we can define it as mu upon rho dAB, where your dAB stands for mass diffusivity of species A and B. This you might have learned in mass transfer 1 and 2. Moving on, mu is the dynamic viscosity and rho is the density of the fluid. Schemate number in GIST can be described as momentum diffusivity upon mass diffusivity. When schemate number is less than 1, mass diffuses faster than momentum, while when it is greater than 1, momentum diffuses faster than mass, in which we have the example of liquids. 1.
So, our next dimensionless number is Lewis number. The Lewis number is a dimensionless number that compares thermal diffusivity to mass diffusivity. It tells us how quickly heat diffuses relative to mass in a medium. Basically, Lewis number is also a ratio of Schmidt number and Prandtl number. So here we can write it as a alpha by DAB, which is K by rho Cp DAB. Okay, so it is basically a ratio of thermal conductivity by mass diffusivity. So here alpha is K rho by Cp, which is a thermal diffusivity. DAB is mass diffusivity of species of A and B. K is your thermal conductivity, rho is your density, Cp is your specific heat at constant pressure, J per kg Kelvin, joule per kg Kelvin. Lewis number, if greater than 1, it means heat diffuses faster than mass. If Lewis number is less than 1, then mass diffuses faster than heat. If Lewis number equals to 1, then heat and mass diffuses at the same rate. As I should mention this, Lewis number have very less use in our topic and in our further calculations.
We can say that Lewis number has very less significance in the coming topic, but we can also write Lewis number as Schmidt number upon Prandtl number. So we have the second last number, that is the Nusselt number. The Nusselt number is a dimensionless number that represents the ratio of convective heat transfer to conductive heat transfer across a boundary. It tells us how effective convection is compared to conduction for heat transfer in fluid system. Nusselt number can be related as HL by K, where H stands for convective heat transfer coefficient. Its unit is watt per meter square Kelvin. L, as we learned in the Reynolds number, it stands for the characteristic length. It is in meter. And K is equal to thermal conductivity of the fluid, that is in watt per meter Kelvin. So Nusselt number can be described in GIST as convective heat transfer upon conductive heat transfer. In the future videos, you will see that we have used a multiple time Nusselt number and the upcoming number, that is the Sherwood number. These two numbers plays a major role in our analogy, which are in Reynolds analogy and Chilton-Coleman analogy. Go.
As we mentioned before, the Sherwood number have a lot of use in our analogies. So when we derive the analogies, transport analogies, we have a great use of Sherwood number, Nusselt number, and the previous numbers, dimensionless numbers, which we have mentioned. So what is Sherwood number? Sherwood number is the mass transfer equivalent of the Nusselt number. It represents a ratio of convective mass transfer to diffusive mass transfer across a boundary. So basically, what is Sherwood number? So Sherwood number is we can write it also. So as we mentioned before, the Sherwood number have a significance in describing and in finding the Analogies. So, what is Sherwood number? Sherwood number is the mass transfer equivalent of the Nusselt number. Basically, Nusselt number is defined for the heat transfer, and now Nusselt number is equivalent to the Sherwood number in mass transfer. It represents the ratio of convective mass transfer to the diffusive mass transfer.
Go.
So, as we mentioned before, the Sherwood number and the Nusselt number having a significant role in describing and in defining the Reynolds analogy and Chilton-Coleman's analogy. So, what is Sherwood number? So, Sherwood number is the mass transfer equivalent of the Nusselt number. So, we use Nusselt number in the heat transfer, and in mass transfer, we use Sherwood number as the dimensionless number. So basically, Sherwood number is the ratio of convective mass transfer to diffusive mass transfer across a boundary. Formula of Sherwood number is KL into L by TAB. K is convective mass transfer coefficient, L is the characteristic length, and DAB is the mass diffusivity of species A in species B. And transport phenomena appears in correlation for mass transfer in following fluids. So in mass transfer, we will see the Sherwood number. And Sherwood number is a function of Reynolds number and Schmidt number. Similarly, in Nusselt number is a function of Reynolds number and Prandtl number.
Go.
So basically, we have brush up your dimensions. So basically, we have here brush up on the idea of dimensionless number. Now we will move forward for the meaning of for the brush up on your topics on physical interpretation of mass transfer coefficient, heat transfer coefficient, and friction factor, from where we will define and describe the transport analogies. Now, we have brushed up on the basics of dimensionless numbers and recalled Newton's law of cooling and Fourier's law. Let's move into our next segment. In this segment, we are going to focus on the physical interpretation of mass transfer coefficient, heat transfer coefficient, and momentum transfer in which friction factor, especially in the context of how these phenomena occur at a molecular level. But before we dive in, just a quick note. We won't be going into the mathematical derivations or detailed theory, since that was already well covered by the previous group. So if you are looking for in-depth derivations, make sure to check out their session. Here, we will keep this conceptual, intuitive, and visual to help you feel what's really happening during these transport processes. Let's begin with mass transfer. So, physical interpretation of mass transfer coefficient, in which Fick's first law, which tells us about the flux, which is NAW is equals to minus DAB into dou CA by dou Y at Y equals to 0, and NAW is equals to Kc into CW minus C infinity. This is your Russell-Luttrell equation, and the above one minus DAB into dou CA by dou Y is your Fick's first law. This both equation will give you the flux. So simply we have equated it and we get the equation of Kc is equals to dAB by delta C. Delta C is your stagnant film thickness. Keep remember this equation. Kc is equals to dAB by delta C. Kc is your mass transfer coefficient and dAB is your diffusivity. This relation will help us in deriving the transport analogy. Now, moving further, we will see the physical interpretation of heat transfer coefficient. So, QW is equals to minus K dou T by dou Y at Y equals to 0, which is your Fourier's law of heat conduction. Then second one is QW is equals to H into TW minus T infinity, which is your Newton's law of cooling. This both will give you the flux. Simply, we will equate both of these equation and finally we will get the relation between the heat transfer coefficient and heat transfer coefficient and H and K, basically thermal conductivity and heat transfer coefficient, which is H is equals to K by delta T. H is your heat transfer coefficient and K is your thermal conductivity. Delta T is your thickness of your stagnant film. Now, please remember this equation and this relation. This will help us in the finding the relation of transport analogy. Now we will move forward for the physical interpretation of friction factor. Here, tau W is equals to half rho V infinity square into F. This is your Finning equation. And tau W is equals to mu into dou V x by dou Y at Y equals to 0. This is your Newton's law of viscosity. This both will give you the flux. Simply, we will equate both of these equations and finally we will get the relation between the friction factor and the Reynolds number. So basically, we will get this Reynolds number is equals to into F into 1 by 2 is equals to LCH by delta. So here F is your friction factor, Re is your Reynolds number, LCH is your characteristic length, and delta is your thickness of your stagnant film.
Thank you, Radha, for summarizing this in gist. I hope you might understand this very well. And if you don't, please refer the previous podcast made by other group members of our batch. Well, now you got a very good idea about dimensionless numbers and physical interpretation of heat, mass, and friction factor. Now we have made the foundation very clear, and now we are ready to build a concept around transport analogy. In the next segment, you will learn about transport analogy, which basically focuses on majorly of two, that is Reynolds analogy and Chilton-Coleman analogy.